All right, so let's begin this video. We will be talking about the practice prob exam for the final exam. This is 90 minutes and there are 7 problems in total, as you can see, 4 short and 3 long. And then, as usual, don't spend too much time on short problems, spend a little bit, but not too much. Yeah, so let's begin and let's get started. So the first question says that surface tension can lead to fascinating phenomena such as formation of tears of wine, as shown in the figure below. So we see this beautiful image where we see these tears of wine on a glass. You can see them very commonly. If the velocity of the tears is u, surface tension of the wine and air is sigma, length of the tear is L, and viscosity is mu of the wine, that would determine which dimensional groups are relevant for this process. So as it's very clear from the text, this is essentially a dimensional analysis problem. And what they're trying to kind of ask is which dimensional group will dictate the process, because we don't know the equations till now in this problem. So we start to count, we have velocity, length, viscosity, surface tension. So we have K is equal to 4. And R is equal to 3, mass length time. So we will get 1. So this should be one dimension. It's just one part. So I'll just start with first method of inspection, just because I like it, I'm biased towards it, but we will also do the full formal analysis. So I see a surface tension, and a surface tension is force per unit length. So I can essentially create a force from it, or I can create a force per unit area. So let's create a force. So it's sigma times L is the force. And then we also know that we have viscosity. And if you remember Stokes' drag, it's 3 pi mu u d. So it's mu times u times a length. And we have only one length here, which is L. It's mu u L. This is the force ratio. So this becomes sigma by mu u. And so this comes out to be the answer. And so if you see these options carefully, I believe this is the one without the L and the correct sign. So this is the one we get. The other option is method of inspection, for which we should just write down. And I definitely recommend method of inspection if you're not very comfortable with this. This force per unit length, so kg meter per second square or kg per second square. This is mt minus 2. Then velocity is length time inverse. Viscosity is mass length inverse time inverse. Hopefully these are second nature to you now. And length is L. Okay, so we'll do sigma. And because sigma is in the numerator in the options, we'll just go with that. So sigma into u raised power of A, mu raised power of B, L raised power of C. So let's do mass first. So mass is only in sigma and mu, so it becomes 1 plus B is equal to 0. This is mass M. Then let's do length. Length is in 3. So we don't have anything in sigmas, but we do have an A, B, and C. So it's A minus B plus C. So A minus B plus C is equal to 0. And then we have time, and time is also in 3. So it's minus 2 minus 1. So minus 2 minus A and minus C is equal to minus B is equal to 0. Minus 2 minus, minus 2 minus A and minus B is equal to 0. Okay, so I've just taken the exponents, and then let's now solve this. So we see B is equal to minus 1 here. It's simple. So if I put B equal to minus 1, and so I get also, as actually if you solve this, you also get A is equal to minus 1. And this also implies C is equal to 0. So we get the same answer, I believe. So we get sigma into mu u here. So you get the same answer. So you can do either approach. I definitely recommend the formal approach if you kind of find it a little hard to do the method of inspection, but whatever works for you. But I wanted to show both the approaches. Okay. So now let's go to the next problem. So it's a pipe flow as the first sentence. An experiment for a pipe flow using water demonstrates that pressure drop is approximately proportional to the average of the velocity. Which of the following statement is correct? You can assume that the pipe is horizontal and the flow is steady and fully developed. You may make use of the Moody's chart below. And so we have given the conditions are laminar in a smooth pipe, conditions are turbulent in a smooth pipe, are laminar in a rough pipe, are turbulent and rough pipe, or the sufficient isn't sufficient. So essentially what the problem is saying, it's a horizontal pipe. So we have the definition of friction factor to be clear. So it says delta P by rho U square by 2 into L by D is my definition of friction factor. So now this is saying that delta P is equal to rho U square by 2 into L by D into friction factor. So basically, if it's saying delta P is proportional to U, because it's saying this is the condition given to us. So delta P is proportional to U, and so it's approximately proportional to the average velocity, which is basically means it's proportional to the average velocity. So then I have a U square. So essentially, I need friction factor because there is no other velocity. I need friction factor to be proportional to inverse of U, right? That's what exactly I need. I need friction factor to be proportional to inverse of U, or essentially I'm saying I need friction factor to be proportional to Reynolds number inverse, which happens in laminar conditions. So essentially I can do any laminar. Laminar doesn't matter, smooth or rough pipe, because laminar condition, as the Moody chart below says, it's it's just inverse of Reynolds number, as you see here, 64 by RE. So that's what you need to make the pressure drop proportional to velocity. If friction factor was, let's say, constant, then the pressure drop will be U square, will go as U square. Or if friction factor had some other exponent of the Reynolds number, such as in the smooth pipe case, we'll get some other exponent depending on what the exponent is or dependency. So in this case, essentially, it's just a laminar flow. Pressure drop is proportional, so you can just go from there, okay? Yeah, so that's it about this problem. So next problem says a creative research assistant is doing experiments in a horizontal pipe flow with steady state and fully developed conditions. They find that friction factor is 0.02 for the regime they're operating in. It seems like it's a constant number. Then the research assistant decides to define a friction factor F nu, which is some delta P d square by mu UL. So it's not the usual definition we see. And the question is, which of the following expression is true? So the point being, F nu is given to us as delta P d square by mu UL, and F usual is given as delta P by rho U square by 2 into L by D, or rather we can say 2 delta P D times rho U square L, I guess. Believe that sounds about right. Yeah. So now the point is I should try to do F nu by F, because that's the way I can try to find the relationship, because I know small f. So I want to find F nu by F. And so F nu by F, and the right hand side answer it is in terms of Reynolds number. So F nu by F delta P d square by mu UL by 2 delta P d by rho U square L. So I can see this delta P drops out. And this L also drops out. So essentially what you're seeing here is you're getting rho U d by 2 mu. This is Reynolds number by 2. I think that sounds correct. This is Reynolds number by 2. So what is F nu? Then becomes friction factor times Reynolds number by 2. And this friction factor is 0.02. So 0.01 times Reynolds number, which means RE by 100. So this is the answer B. Okay. So this was a kind of an interesting problem, just sort of redefining a new friction factor, but you are allowed to define it. Like we said, we choose this definition because that's it's just convention. You can define something new, So yeah, that can it just works out this way. In this case here, basically we were trying to look at the relationship between friction factor and different, sort of exponential velocity. Here we are more interested in the definition of friction factor. So, all right, let's keep going. Then the question is, Blashes' result on boundary layer over flat crust suggests that FD is equal to 0.006 for this. This is being kind of given to you. Length is the length of the plate, means this is this. What is the value of skin friction coefficient CF is equal to this? And you're given that Reynolds number is equal to rho U L by mu. Yeah, I mean, it sort of seems like a very, it's like a plug kind of question. So you do 2.62 into 0.664 width of rho mu U cube L by W rho L U square. And so this cancels out. Interestingly, nothing else cancels out directly because you get a, so basically you kind of say 1.328. You take everything in the square root, rho L square U4. Yeah, I mean, this is pretty simple. You just get mu by rho UL. This is 1.328 into RE to the power of minus half. Yeah, so this is just this the last option here. So this is what you get. I mean, it's pretty easy plug and chug kind of question. Yeah, I mean, this is just a Blashes solution trying to show some sort of a like a drag coefficient, like a skin friction coefficient, defining something similarly. Yeah, this is it for the short problems. So now let's go to the long problems. So the question here says that consider a pendulum mass m hanging with a rope of length L in the liquid of density rho and viscosity mu. The time period of oscillation is T. The gravity symbol is denoted with G. Okay. So find a dimensional group that govern the system. You can either use formal analysis or method of inspection. So this is sort of like, what I was saying, viscous damping can affect, your system. So that's, I think, the basic idea here. And so how many variables we have here? So 1, 2, 3, 4, 5, 6, 7. These are a lot of variables. So we get K is equal to 7. K is equal to 7. And then R is equal to 3. We'll have 4 dimensionless groups. So yeah, I mean, one can technically just dimensionless groups using some sort of yeah, like a inspection method. Let's just first do that because I personally like it. So pi 1, I mean, I see 2 lengths, so simply d by L has to be 1. Pi 2, so 2 lengths should be 1, and then I have a mass and I have a density and a distance. So, mass by rho d cube. I have to be a little careful sometimes. Sometimes you don't end up, if you're a bit careless, there can be a mistake. We also know that I mean, this is sort of more like knowledge rather than something you may not necessarily remember, is that time goes the square root of L by G. So, why not T by, I'm trying to use all of the variables. So time by square root of L by G is pi 3. And then pi 4, I think should be a good old Reynolds number. So, I think it should simply be the rho. I don't have velocity, but I can make velocity using d by time. And then I can have d by mu. I believe I should have used all the variables. So this is just method of inspection. This is my style to do this. And hopefully you're also learning, even if you're not comfortable with it, like how one can think about it more broadly. Okay, so these are the dimensional group I have done from method of inspection. But let's do a formal analysis, which might take a bit of a time here. So we want to choose 3 variables which are repeating because there are 4 variables which are non-repeating. So let's just take the repeating variables to be, and we want to cover everything. We're going to cover mass, length, time. So I think we can just do rho. Rho has mass. We have length as repeating, and then time as, again, a repeating one. Not the most ideal, but I think it's not bad either. So yeah, we can just do this. And so let's start with, so repeating variables are rho, L, and T. And then now for pi1, I'll start with M. So let's start with M. So M into rho raised power of A1, L raised power of A2, T raised power of A3 is equal to, should be dimensionless. And so this becomes mass is just simply mass. Rho is ml minus 3 times. Actually, let me just do it more properly. So m is mass, rho is ml minus 3, length is L, and time is just time. So we do this. So when we do mass, we say mass is only present in two of them. So it becomes, for mass, it becomes 1 minus A1 is equal to 0. Rho, sorry, length, MLT. So length is present only in the density and the L. So density has minus 3, so minus 3A1 plus A2 is equal to 0. And time is just present in only one of them. And so this was A3 actually, so A3 is simply 0. So yeah, I mean, it's pretty simple to see this kind of looks like what I had one of them. So A1 is equal to 1, A2 is equal to 3, A3 is equal to 0. Yeah, I made a small mistake here. It's 1 plus A1. I sometimes do this mistake. It's 1 plus A1, so it's just minus 1 and minus 3, just a small correction. Minus 1 and minus 3. And so this gives you that pi1 is m by rho L cube. So you can see sort of a similar one here, but the difference being that it's by d cube, but that's just because there will be another length of, L by d. So that's really easy. So mass m is done. So now let's do d, because d is also an easy one. We don't need to do it too much. So d into rho raised power of a, b1, b2, b3, b1, L raised power of b2, t raised power of a b3. And this should simply just give you that b2 is equal to minus 1 because of length, and because of mass and time, b1 and b3 will come out with it. This is pretty simple. So we'll get pi2 is equal to 1 d by L. Okay. So this is the second method, second option. Then the third one, we have still not done. So we've done mass and d. So we're left with gravity and viscosity. Okay, so let's do third being gravity. So gravity is gravity rho C1, L C2, T C3. So for this, for mass, we only have mass in density in this case. So this will simply imply C1 is equal to 0. So there is no mass in anything else. Then lengthwise, we do have it in a meter per second square. So we do have 1. Then we have plus C1 because we also have an sorry, our density is not there, but so I will not write it, but you could. Then we have length as 1, C, 2. So we get this. So sorry, just to kind of be sure. So this is meter per second square, and so meter, yeah. So 1, and then length is simply 1 plus C2 is equal to 0. Implies C2 is equal to minus 1. And then I have time. So the time one becomes meter per second square. So T2 minus 2. So minus 2, then length does not have any time, then we do have time, which is plus C3. So this implies that C3 is equal to 2. So basically, yeah, so this gives you GT square by L, essentially. So this is your pi 3, which kind of looks like, the square root of L by G, kind of whatever idea I was saying. So it is similar, just it's you just square it, then you will get this one. Yeah, so last is pi 4. Pi 4 is the viscosity. So we have mu, then we have rho d1, L d2, T d3. And so mass is only in mu and rho. And so it becomes ml minus 1, T minus 1. So 1 plus d1 is equal to 0. Then length is in quite a few of them. So we have 1 minus 1, ml minus 1, because, and then length cube density minus 3d1 plus d2 is equal to 0. And then time would give you something else as well. Mass, length, and time. So time is there only in mu and the other one, the t. So mu is ml minus 1, T minus 1, so minus 1. And then time is simply this, so d3 is equal to 0. So d3 is equal to 1. D3 is equal to 1, and then I get d1 is equal to minus 1. D1 is equal to minus 1, so plus 3 minus 2, so d2 is equal to minus 2. So this is what we are getting. So sometimes can take a while to do these things. So let's just do that's find pi 4. So this is mu by d1 mu t by rho L square. Yeah, I mean, this kind of looks like that, right? So I had mu L by T or D by T rather. I mean, so I was just a ratio coming on the length D by T times D. So it is rho D square by mu T. So mu T by rho L square. Yeah, this works out completely. So you get 4-dimensional groups and it works out. Okay. Now the question says the equation of motion for the position X of the pendulum is given by this. So there's some position X equation we have been given. So to non-dimensionalize, we are asked to define this numbers. Fd is equal to this, t is equal to d by tau. Okay, so question really is what's the value of tau? So the main question here is what's the value of tau? The dimensionless groups. So I mean, if you're not comfortable, but I believe we did discuss this. So this will become md d square x tilde by tau square d tau square is equal to minus mg and then mg and then plus fd. This is essentially, I've just substituted. Remember that x is equal to, so essentially this is telling us that x is equal to x tilde d and time is equal to t tilde tau. So just use that. There's a square here because there's a second derivative. And so to make ft tilde, I just need to divide by mg. So I divide by mg. So it becomes d by t square g, t by tau square g, t square x tilde by d tau square is equal to minus 1 plus f d tilde here. So this number has to be 1. So that means tau is equal to square root of d by g. Yeah, I think that sounds about right. So that's the value of tau, which we are able to get that from the system. And I was just checking the units in my head. This is a meter by meter per second square root, so it becomes second. So it's just simply root d by g. So that's just like a dimensionalization of the equations problem. But here you can see we have a sort of a buoyancy factor almost, mass by rho d cube here, a Reynolds number coming here, some sort of a time period based on the without the drag coming here, and the ratio of lengths coming here. So it's just good to appreciate some of the numbers that you're getting. Similarly here, time is coming out to be the right unit, just to kind of sanity check. All right, so let's keep going. So now it says, consider a pipe network below. Water flows from a very large tank through a series of pipes. All the pipes have length L, diameter D. Okay, so all of them have length. The 90-degree bends in the pipe are regular and threaded. The loss coefficient on the time is negligible, so there is no loss here. No loss here at the inlet. Tank is at height h above the outlet. Okay, so height is h. Both tank and outlet are open to atmosphere. Gravity is going to be symbol G, and the viscosity is mu under stereo. Okay, so find the flow rate Q into the system if all minor and major losses are neglected. Okay, so basically they're saying just apply Bernoulli's. So we'll take 0.1 to be this, 0.2 bit or in and out rather. Let's just do that. In and out. So the P in and P out can be 0 because they are both PATM. So we can say P in plus, there is no velocity because a large tank, as we have discussed before, there's nothing there. So this is P in by gamma, by the way. I'll just use the units we've been using, plus H. So we'll define this as Z equal to 0 is equal to P out by gamma plus U square by 2G. And then there is no loss here because no losses have been asked. And then there is no height because Z is 0. This cancels out. So U simply becomes root 2GH, which is kind of what we have done before. So it's simply saying that, just multiply with square root 2GH, free velocity of open channel. So without any losses, it doesn't matter. It essentially is saying that all the potential energy gets converted into kinetic energy. So you get equal to root 2GH. Oh, find the flow rate rather. So apologies. So then it says Q1 is equal to U times pi d squared by 4. So this is root 2GH pi d squared by 4. So it's a simple problem. That's what you get. All right. Then next, you're given flow rate Q2 through the system is both through the system if both, I think if both major and minor losses were to be accounted for. You're also given that the flow condition is turbulent in a very rough pipe, such that the friction factor F is this, and it is just filed in the value of Q2 by Q1. Interesting. So basically, it's saying that we'll just start to add losses now. And so, you can still say H is equal to U square by 2G, but we still now have to add U square by 2 into, losses essentially. So the losses, I believe here are like the 90-degree bends, which I think the problem alluded to. The 90-degree bends in the pipe are regular and threaded. So there are 3 bends, so we should go with that. And then at the bottom, there is a table. So regular and threaded, so we'll take 1.5 here. So 1.5 into U square by 2. But then we also, U square by 2G rather, sorry, there was a small error here. U square by 2G. But then we also need to add 3 times KL. So this is the loss for that. And then is there any other loss that I'm missing? So 3 90-degree bends essentially. And then it says don't neglect the loss from the inlet. And so you just need the major losses now. So I have FL by D, U square by 2G plus FL by D, FL by D, FL by D. All the pipes are the same, F and L by D is the same. So you can simply say 3 times, 3 times FL by D. So you essentially get U square by 2G into L by D is 50, 3 into so the regular and threaded. So just to make sure we are getting it correct. Yeah, regular and threaded. And so it's just basically all we're saying is 3 into KL. So 3 into 1.5. F into L by D is 1 because this multiplying is 1. It's also 3. And then I also have the plus 1 from the first one. So 1 plus 3 into 1.5 plus 3. So this becomes U square by 2G into 8.5 into H. So, your velocity 2 rather, I will just call it velocity 2 is, H by 8.5 into 2G square root. So Q2 by Q1 really is simply, at U2 by U1 because, the size is the same of the pipe. So you just get 1 by square root of 8.5, and approximately 1 by 3, approximately something like that. All right, so now it says the third problem says for the same F and L by D values, an engineer suggests that to minimize losses and increase the flow rate from Q to Q3 from Q2, one should remove all the 90-degree bends. So the idea is we'll just remove these 90-degree bends while keeping the total length the same. So that makes sense. So basically saying instead of like going like this, we just kind of slant or something. Oh, and so yeah, however, in doing so, the total height difference is also reduced. So you get 0.75 H there. And the question is, do you agree that the flow rate will be increased? So really, the question is saying it's the left-hand side is reduced by 25%, but then is the gain enough to compensate for that? So we have 1 plus, 1 plus 3 already. Now you get H implies Q to be U3 rather in this case. So U3 should be, yeah, because 3 is still the same. Length is the same, friction factor is the same. So instead of, you basically get 4.5. So 0.7 by 4.5 square root of 2GH essentially. So U3 by U2 really is, so U3 by U2, we should divide by that. So it's basically 8.5 into 0.75 by 4.5 square root. So it is greater than 1. So you would see increase in flow rate, I think. Yes, so you should see increase in flow rate because this is greater than 1. Now, because you minimize, it seems like a lot of loss comes from this KL actually, which is pretty high. That's why I was checking again the table. Seems pretty high. It is 1.5. Maybe if it was flanked, then you would get something else. 0.3, which will really reduce the the losses. So yeah, so the velocity increases because they are threaded, and so you remove the losses or you compromise a little bit on driving force. You were still able to kind of get the flow rate to increase. All right. So let's keep going. So then last question is, an athlete is racing in boulder and decides to accelerate by propelling with the force this. So some athlete is running, propelling force is 20 Newton. The density of air is this, viscosity is this. The athlete is 70 kg and is a density of 1000 kg per meter cube. So what is the maximum velocity that the athlete will be able to achieve if they cycle while sitting upright and cycle while bending in a racing position? So basically, I think the maximum velocity means here the velocity with the forces are balanced. Forces are balanced. So I'll sketch a very bad kind of free body diagram here. The person is like this. So you're propelling yourself by applying a lot of energy by FP, and then there is a drag here. So when FP is equal to FD, that's when you sort of get the. I mean, you can do the acceleration problem. Essentially, that's the idea. So the FP is equal to rho u square by 2 into CD times area. So this simply becomes u is equal to 2 times FP by rho times CD times area. And this essentially becomes your velocity. So for when they're sitting upright, this becomes square root of 40 and divided by 1. Rho is 1, right? Density is 1, air. CD times A, so 5.5. So 40 by 5.5. So I'll have to check the value here. Square root of 40 by 5.5 is 2.7 meters per second. So this comes out to be 2.7 meters per second. The velocity in the second case should be larger because it is a smaller CD times A. It's 40 times 0.36 into 0.88. So that comes out to be something else. So let's look at 40 times 0.36 into 0.88. Actually, I apologize. There was a small error in my calculation because that's what I was realizing. It's not 0.5. It's I basically missed a factor here. Is 0.55. That's why I was. So let's do this. So 40 by 0.55 first. As you can see, I'm doing this on the fly, so I do also make mistakes. So 8.53 meters per second, and that sounds more reasonable for a biker. And then 40 by 0.36 into 0.88. So 0.36, 0.88. Hopefully this should come out to be larger. This is 11.2 meters per second. So that's sort of the simple force balance and calculation. And then athlete is at the velocity of 5 meters per second, but now suddenly sees that there's a truck in front of them. Okay, so they'll accelerate, there's some velocity. Which position would they adopt to decelerate faster while applying brakes? How much time would it take them to reduce their velocity to 1 meter per second? So here the concept comes from the deceleration part, basically, that now when they are applying, they're not going to propel because they want to decelerate. So just the drag should be like this. And so we're saying m du by dt is equal to minus CdA rho u square by 2 CdA minus rho u square by 2 CdA. And so you can integrate this, and I believe this. I'll just quickly do this because I've seen these kinds of integral before. It'll be 1 by u plus 1 by u naught plus rho CdA by 2m times time. So this is essentially what you get as your answer. Now, the question is which position should we use? So we want the velocity to reduce faster and without applying brakes. So we obviously want to increase the drag, and to increase the drag, basically which position? So we should kind of do the sitting upright position. So sitting upright. And the question is, how much time will it take them to go from 5 meters per second to 1 meter per second? So this is, now we'll substitute. So you get a 1 by u minus 1 by u naught into 2m by rho CdA is equal to time. And so 1 by u is 1 minus, so this is 0.8 into 2 into mass. I think mass was given. This is 70 kgs into 70 by CD times A. So rho is 1, so CD times A is, we have to use this one, so 0.55. And this is equal to time. And so this is actually a pretty long time, clearly, which is not great, but that's without applying brakes, that's what's going to happen. So 1.6 into 70, 1.6 into 70, 5.55. So it comes out to be 203, 204 seconds. We'll just say 204 seconds. Approximately, it's about 3.5 minutes or something like that. So you kind of get the sense from this. Yeah, so this was a deceleration question, a relatively easy one. These were pretty straightforward. Yeah, so this is the entire exam. I hope this was helpful. Yeah, feel free to let us know if you have any questions, and hopefully this is helpful for final prep.